All right, so when we left off last time, um, we were showing graphs here for endothermic and exothermic, and it was highlighting that energy can go in or out of a system, and in the process it can change form. Like for example, if we wanted to just talk about light energy, it's possible that we could do some type of chemical reaction that would start off with, say, the reactants being something at a little higher energy state, and we go through a process and we end up at lower energy. And it could be light that's given off in that process, it could be heat. A lot of times in this we do think of it being a flow of heat, thermal energy out of the system. But it could be a lot of things. This one, the opposite situation, you'll notice that it starts out lower on the reactants and then ends up higher on the products. So we still have to put this activation energy in to get the reaction going in many cases, in fact all cases. But the end result is that we have an increase in the flow of energy into the products. This would be like the sorbitol lab that we did. The products ended up higher than the reactants. So anyway, this is an example of what we would consider an exothermic reaction here, where the delta H is an output of energy from the system. And then, of course, if it's an increase and a put in, that would be an endothermic reaction. And it's real easy to get that confused because you got to remember what point of view to keep it from. Typically in chemistry, it's from the point of view of the chemicals, the reacting chemicals. So in that first law, we were basically saying energy can go in, energy can go out, but the system and the surroundings always exchange energy without really losing energy, which most of you are familiar with. But the second law is a little bit more subtle, and we've got it up here. The second law of thermodynamics doesn't say that energy that goes in and out is always conserved. It implies that. It knows that is true. But it does say that if you are, no matter what kind of transfers you're doing or what's going on in any closed system, there cannot be an increase in the available energy, not a net increase. In other words, you can't ever find a way to have more energy than what there was there. If you bring it in from outside, then yeah, there's more in a certain part of the system, but you can't create any. But this is the big part. Any process that occurs in a closed system will result in less available energy. Now, this is, some people talk about this law, the second law, as being what we think of when we think of efficiency. In other words, there's no process that you can do that is 100% efficient. In fact, what this law is saying is there's no process that you can do to even break even. A lot of physics classes will teach that way because that's an outcome of this. But most of us are really aware that as processes go on, there are losses. Like, if I clap my hands and you say, oh, sound, so some energy went out in the form of sound. There's energy in the form of heat. And I suppose this is not a bad example of what we're talking about. I ate my lunch, and there was a lot of available energy in my food, and as that process goes on, I wasted a lot of the energy I ate. I wasted it as heat that just gone off to the surroundings, or I just did that. And how can I get that energy back from that clap or from the little bit of heat that goes off? So what they're basically saying is that everything is that way. Everything will have less and less available energy over time. Not necessarily less energy, but it would be not a form that is usable. You know that the earth would run down if left to itself. So we know that energy can't be created or destroyed, but things will run down and not have usable energy available over time unless there's some other input that's made. For example, in this case from the sun. In chemical systems, you will have something that's very high quality fuel, or maybe you have oxygen, a pure element or whatever. And as these come together and combust and energy is given off, you're going to see a lot of times like mixing together and becoming disordered and more random is an outcome of this. And there's a word for this disorder and lack of usable energy in the system. This increase of this disorder is known as entropy. And that's really what the second law is about. If the first law is about heat can flow in and out and energy can change forms, if the first law is a law of enthalpy, which primarily I suppose you could relate those two things most closely, this one is really a law of entropy, that even as all these changes are taking place, you always end up with more disorder and less available energy. There are a few things here that we could say about this that are kind of a little bit interesting. This kind of implies that if this is always happening all the time in any closed system, and the universe is a closed system, that the entropy of the universe is constantly going up. That means basically that eventually things that are present in the universe will become all blended together. All forms of energy will convert to random thermal energy that's just like an even temperature and evenly distributed. And if you think about it, that's what everything tends towards if left to itself. A lot of people actually refer to this as what is known as the heat death. So basically what the stars are doing, where they are producing electromagnetic radiation, which is a form of energy produced by the fusion reactions we believe in stars, that goes out, and there are living organisms like plants that capture that energy and convert it to food for our use, and they also produce oxygen, and so they do the photosynthetic process. But if you think about it, during all of this process, there is the cow eats the grass, and a lot of the energy that was in the grass gets converted to just heat from steam coming off the cow while it's out in the pasture field. I mean, you can just look at all these wastes and these losses of energy that just occur as all these processes are taking place. And if that goes on long enough, and it's a closed system with no input of energy, everything will get converted to random thermal motion, and there'll be no separation of charges. Everything will just be randomly mixed, and there'll be no potential energy available, and the universe would be unable to run at that point. It's interesting, it does imply quite clearly that the universe was sort of started with this amount of energy, and all of the energy is still here. That's what the first law says. But the second law says it's all converting to forms that are not really particularly useful to us. Disorder is becoming greater, and the usable forms of energy are going away. So that's kind of the second law. So when you're dealing with systems, you can kind of talk about entropy as a synonym to disorder. How much organization and separations within the system. With regard to chemistry, a change in entropy will show up like perhaps as disorder of molecules. If you want to look at that as just, it's only one example really of entropy, but as gases spontaneously would spread out and diffuse in a container and become evenly mixed together and fill up their entire container, they're seeking the most likely state, which is the most disordered and randomly mixed state possible, and they're going to do that. A person might say, well, do they think about that? And the answer is no, obviously, even though we talk about these things like they have some personality to them. The truth is that they're just going to the state of greatest probability. So that also plays into entropy. It's just what are the odds of how it's going to be, and there's more ways for it to be spread out and disordered than is to be like over in the corner and organized. So when we look at chemistry, we will look at this idea of randomness or mixing, or are the molecules becoming more disorderly. Becoming a gas is a great example of something that generally implies that entropy is increasing. Because it is a measurement actually of disorder, if you have an increase in the entropy, it means it's getting more disordered. It is an energy measurement, entropy is. Enthalpy is most certainly a heat flow, it's an energy one. So is entropy, a form of positional relationship. The entropy is a really broad concept. That's why we kind of try to simplify it down in chemistry and just kind of say, look, it's the mixing or the disorder, and that does have a certain energy associated with it. For example, like I was mentioning a second ago, gas, you would, in your mind, you would see that as a more disordered state than, say, a solid. Typically, these are given in joules per Kelvin, so obviously the amount of entropy that's present depends upon the temperature that is there, and it is always the absolute temperature scale. And sort of in general, the temperature, the higher the temperature, the greater the entropy. Now, that brings me to a sign thing here that I need to touch on real quick, and a symbol deal. The symbol for entropy is S. So on the screen here you can see we have delta S. That literally translates to change in entropy. I honestly, off the top of my head, do not remember where that letter came from to be associated with this term. Be a good thing to Google maybe. But if it is a positive value, and we've talked about, you know, if energy is flowing into the system in the terms of an enthalpy change, that a positive means endothermic and coming in. This indicates an increase in the disorder of the system. An entropy change that is toward more disorder is positive. If the entropy were to become decreased, in other words, if the system became more ordered, then the sign of entropy is negative. So you really need to kind of get that in your mind, that entropy is disorder. Therefore, if things become more disordered, that's a positive entropy change. And of course, the opposite is also true, as it is with most thermodynamic things. It's going the other way if it has a sign change. So the second law has a mathematical expression that we'll introduce to you here that's valid. If a system is at equilibrium, so let's say that we have some salt that's dissolved, and it's reached a place where the crystals have all broken down, and if it's a saturated solution with crystals in the bottom, one could even argue that it is dissolving just as fast as it's recrystallizing, and that's why it's reached a balance here. And for situations that are at equilibrium, there is a relationship between enthalpy change and entropy change. The change in the heat, which we would think of as delta H, as long as it's a constant pressure situation, is equal to the temperature times the entropy change, T delta S. So mathematically, it's a very interesting thing that's going on. So at a particular temperature, the delta H could become equal to T times delta S. You know, clearly that could happen. Some number there is going to make that work. And I'm not going to go into a lot of detail now because this video has gone on long enough about the second law. But that has a lot of effect on phase changes. And just to wrap this up, take a look at some entropy situations where you might be able to talk about, well, what's going on with the entropy just by looking. Here on the screen you'll see I have NaCl solid, and it's becoming Na with +1 charge, which actually it already had a +1 charge, but it's just becoming aqueous and separated from the chlorine. So you know, what is this process called that we got going on here? And I hope you would agree that specifically this is salt dissolving. That's what it is. In general, this would be a dissolving process or a dissociation where the ions are becoming separated, in this case by some water molecules. And so the question for us becomes, do you think this is an increase or a decrease? Since I'm just about out of time for this video, I'm going to tell you that this is an entropy increase because the ions are being broken apart, the crystals being torn apart, and we are having a greater disorder by having these free ions than we did before, and this is a delta S plus, which is an entropy increase. So catch you later.